Mathematics operates on a Cartesian dualism. On the left is syntax, the reasoning process represented as uninterpreted symbolic operations carrying no physical dimension. On the right is semantics, the concrete sets, spaces, and geometries constrained by specific equational laws. This creates a structural tension. We need to identify the mechanism that allows raw, uninterpreted notation to pass through a specific filter of axioms to generate a rigid mathematical structure. We cross this frontier by constructing a free algebra. This is a structure that satisfies a given set of laws while remaining as generic as possible. It serves as the functional bridge between pure logic and algebraic reality. Construction begins with a base set of arbitrary variables, which we denote as x. These variables are the primary building blocks for the entire structure. From x, we generate a term algebra. This operates on a purely syntactic level. In a term algebra, an operation like x plus y does not calculate a value. It simply returns the concatenated string x plus y. Because no laws have been applied yet, the string x plus y is a different object than the string y plus x. This unconstrained concatenation forms what is called the free monoid on an alphabet. A monoid is an algebraic structure with a single associative binary operation and an identity element. In this free version, the variables act as letters, and the only identity is the empty word. Geometrically, the free monoid appears as an infinitely branching tree. The internal nodes represent the operations, which are limited only by their arity, the fixed number of arguments they can accept. The leaves of the tree are the generator variables from our set X. At this stage, the term algebra represents unconstrained potential. It is the raw material used to build structured mathematical spaces, restricted only by the basic rules of the language itself. We move toward a concrete model by applying a quotient. A quotient is a process where we take the infinite syntactic tree and identify specific different terms as being equal based on a law. We can analyze this using a term algebra generated by two variables, x and y. Without laws, every path creates a unique branch. Now we apply the commutative law, identifying the string xy with yx. Structurally, the tree merges these separate branches together. Consequently, the order of symbols no longer carries information. Term identity is determined strictly by the absolute count of its variables. This collapsed tree rotates 135 degrees into a coordinate grid, forming the upper right quadrant of the Cartesian plane. This free commutative monoid on n generators is equivalent to n to the n, the space of tuples of natural numbers. This shows how algebraic laws act as physical constraints, instantly translating infinite syntactic trees into perfectly rigid, stable mathematical grids. A different structural shift occurs when building a free group. This requires introducing inverse variables for every generator, like variable a and its inverse, a. Our starting point is now a 4-array tree. The root has a degree of 4, and every subsequent node has a degree of 5, 1 incoming edge and 4 outgoing edges. Applying the inverse law deletes adjacent complementary pairs. In our tree, these edges annihilate each other, forcing parent nodes to merge with descendants. These cancellations homogenize the graph, dropping non-root node degrees from 5 to 4, turning the tree into a uniform lattice. This uniformity means that no single vertex is structurally unique. In a free group, any point in the lattice can serve as the mathematical identity. These specific examples of collapsing trees point toward a general rule for all free algebras, defined by the universal property. Set X generates a free algebra, B, next to a target algebra, A. A valuation function, f, maps our variables to values in A. The universal property guarantees a unique homomorphism, H, extends this mapping to the entire free algebra. Because this map is unique, internal variable identities are irrelevant. Only the total size of the original set X determines the free algebra's final structure. This property demonstrates that free algebras are determined by their relational mappings, providing the most general way for generators to interact within specific laws. This bridge between syntax and semantics is formalized within category theory. Category theory is the study of mathematical structures and the relationships between them. We can visualize this as two separate planes.
On the left is the category of sets, which are discrete and have no internal operations. On the right is the category of algebras, where elements are constrained by laws. Our valuation function, f, is a map that leaves the category of sets to reach the underlying elements of an algebra. The homomorphism, h, is a morphism that stays entirely within the category of algebras, preserving the structure from one algebra to another. There is a precise one-to-one correspondence between these two types of maps, known as a categorical adjunction. This formula proves the way we build a free algebra from a set mirrors extracting a set from an existing algebra. Adjunctions provide the translation layer between different mathematical universes, linking the logic of uninterpreted sets to the geometry of algebraic structures. This translation is driven by two tools called functors. A functor is a map between categories that preserves the composition of morphisms and object identities. Functor F is the left adjoint. It takes a raw set and builds the syntactic structure of the free algebra. The forgetful functor U is the right adjoint. It does the opposite, stripping away the algebraic laws to leave only the underlying set of elements. We are left with a reciprocal relationship. Functor F creates structure from logic, while functor U reduces structure back to logic. The mechanical collapse of the trees and the arrows of the universal property are the observable effects of these functors in operation. Free algebras prove that algebraic structure is not an inherent property of elements, but a consequence of universal mappings connecting discrete sets to semantic domains.